Hi there. My name is Deepak Sundaram, and this is my presentation on the role of metallicity in star formation and stellar evolution. Before I go on, I'd like to give a quick thanks to my Polygence mentor, Sophie, as she helped me a lot during this presentation and helped me do lots of the research for this presentation and my paper. So now a quick background on star formation. All stars originate in molecular clouds. These are clouds of gas and dust in the ISM. This is a picture of one of the millions of molecular clouds. Molecular clouds then undergo gravitational collapse, which is when gravity forces them to collapse in on themselves. This raises the internal temperature of the star and creates very dense regions. In these dense regions, a protostar then forms, and when the protostar gets hot enough, it undergoes nuclear fusion. Nuclear fusion is when the protons of an atom fuse together and release a bunch of energy. This energy release is eventually can balance out the force of gravity on the protostar, leading the protostar to become stable. The protostar will then remain like this for the majority of its life. So, how does metallicity affect star formation? And why do we care? Well, stars are the basis of life. They contained all the material that will ever be in the ISM, and they contain the material that created Earth, us, and the entire solar system. So you can essentially say we are made of stardust. Stars also are the only reason life can ever exist. So without them, there is no chance of extraterrestrial life. Now, metallicity affects how stars are structured and evolve, which could potentially affect planetary systems and future life. The current prediction on how metallicity affects star formation is a predicted increase in low-mass stars such as our sun. Now, star formation. As I said before, stars all originate in molecular clouds, such as this one right here. These are giant clouds of gas and dust, mainly hydrogen, and they can reach temperatures as low as 10 K. Then the molecular cloud undergoes gravitational collapse, which is mostly caused by external sources such as supernovae, which is the explosion of a dead star. This, again, increases the internal temperature of the star, which creates dense cores. As the cloud collapses, however, it fragments into several pieces due to a process called fragmentation. Each of these pieces has a potential to form a star and its own planetary system. Then, in the densest regions, a protostar forms, which is a small yellow circle. This continues to collect mass by gravitational attraction. While the protostar spins, a large disk forms around it. This is called an accretion disk. This disk feeds the star with gas and dust and is the birthplace of planets, as there are millions of rocks within the disk, and over time they clump together to create planets. Now, as this is going on, the protostar undergoes nuclear fusion. Fusion starts when the core temperature reaches 10 million Kelvin, and as I said before, it causes protons to fuse together. In this case, it causes hydrogen to fuse into helium, and it marks the birth of a main sequence star. Finally, the star reaches a point where it is stable. This is called hydrostatic equilibrium, and it is where the energy generated by nuclear fusion can balance out the pressure of gravity. The star will then remain in this steady state for the majority of its main sequence life. Now, you may be wondering how metals form and disperse in the ISM. Well, metals mainly form in a process called nucleosynthesis. In this process, metals essentially get cooked into heavier ones through a series of nuclear reactions. The higher mass a star has, the stronger nuclear reactions it will have, resulting in a wider range of elements, such as gold and diamonds. Now, metals disperse through the ISM in several ways, but mainly through supernovae. Supernova is when a star explodes, and this, as you can see in this picture right here, when a star explodes, all the elements within the star get spread out through the ISM, allowing other stars to be born. Now, metallicity also impacts the strength of the magnetic fields of a star. Metals within a star's core cool the gas around them, create denser regions with higher electrical conductivity. These three effects all increase the strength of the magnetic field of that star. Now to the main point. How does metallicity affect star formation? As stated before, metals within a star's core act as cooling agents. And this change in temperature also not only causes color difference, but also causes fragmentation. Metals in a star also make the star more opaque, which causes less energy to be transferred within the star, causing the temperature to drop. This is similar to greenhouse gases on Earth, as on Earth, the greenhouse gases allow heat to pass through the atmosphere, but not leave. In the star, however, the metals don't allow the energy to enter the star. This slows down nuclear fusion as less energy can be transferred, which increases the overall lifetime of the star. As mentioned before, the change in temperature also causes color difference. The star on the left is a red and yellowish star, and this is a relatively low temperature star like our sun. On the right, however, we can see a very high temperature star, which is why it is blue and white. Finally, metallicity can also affect how much mass a star loses. As stated before, metals within a star can create stronger magnetic fields. This causes stronger solar winds. Solar winds are when a star ejects energy and mass out from itself, like here. Our sun does this a lot. This ejection lowers the mass of the star, making the star fall on the HR diagram. The HR diagram is a way to classify stars based on their spectral type and magnitude or brightness. To conclude, metallicity plays a very important role in the process of star formation and the evolution of stars. It influences not only its formation, but also its lifespan, structure, and eventual fate. By studying metallicity in stars, scientists can determine if a star has the right elements to create life and if extraterrestrial life is even possible. Now, these are some of the many sources I've used to create this and my paper, and I hope you enjoyed my presentation. Thank you.